So, hello everyone. Welcome to the September AWRI Seattle chapter meeting. Again, we're doing this meeting virtually, so hope you all by now are very familiar with our format. So, in our meeting today, we're very excited to have Dimitrios Athanasiou. You're gonna have to pronounce your last name for me. Sorry. He's been doing, there you go. Yeah, I'm gonna let him introduce himself, but from what I've heard from him, he's been doing really fascinating work on stormwater runoff chemistry and some lab work. Dimitri actually just came back from Alaska, one of his field trips. So really excited to have Dimitri present for us. Again, our meetings are recorded. We typically post those meetings on YouTube for those who can't make it. The link to the YouTube channel is here. I'm going to post it on the chat if you want to go and check our previous recordings. So as you probably know, if you have any questions during the presentation, feel free to raise your hands or post your questions in the comments. And I'm going to keep the questions toward the end unless someone is having any technical difficulty or if they can't hear us for whatever reason, please let me know and I'll jump in and interrupt Dimitri. So that's all I have. So with that, I'm going to stop sharing my screen. I'm going to pass it to you, Dimitri.
Excellent. Thank you very much, Simon. Can you guys see my screen now?
Yes.
Yes, sir.
Perfect. So thank you very much, Simon, for your introduction and your kind words. And thank you, everyone, for attending this presentation. My name is Dimitrios Athanasiou, and today I will talk to you about a project that I worked on for more than 4 years during my graduate studies at Texas Tech University. So the project in discussion is ER2428, as you can see on the top right of the screen, and you can Google it as such, and it will come as the top result. So this project was funded by CERDA PSTCP, who, in their own words, they are the Department of Defense's environmental research programs. So effectively, it's their divisions of the Army that they are focused on doing research on, of course, on topics that are relevant to the Department of Defense. Now, the main entities that conducted the work and research on this project were Texas Tech, where I was part of back when the study happened, SPAWAR in San Diego, and Geosyntec. The PI of the project was Dr. Danny Ribel from Texas Tech, who is an established expert in contaminated sediment research. Now, why would the DoD fund an over $1 million project on the effects and recontamination potential of stormwater runoff on sediments? And again, in their own words, sediment contamination for the DoD constitutes a $2 billion liability. And any remediation efforts for this liability from the part of the DoD should be fortified with minimizing any recontamination potential. And after all, you don't want to clean something up, a liability that you have, only to have it becoming dirty again, very shortly afterwards. Now, stormwater and the runoff that it generates is a mode of environmental pollution that is of especially high importance in big coastal cities. And depending on the data source that you're looking, 30 to 40% of the US population lives in coastal counties in general. And from what I remember from United Nations data, I think worldwide it's about 40%. In my country, from Greece, where probably 80% of the population lives right next to the sea. Now, urban areas, due to the high percentage of the impervious surfaces that they have, stormwater runoff has the potential energy to transport particles deposited on the pavement and on, driveways, parking lots, and even rooftops, and all other paved surfaces, to transport them into a receiving water body, effectively in the end, through a conveyance system that is part of almost every coastal city. Okay. Now, such particles that are transported, that are mobilized and transported by the runoff itself, can be in an urban environment like pieces of tire, pieces of asphalt, of soot, and particles that they often tend to be coated with, gas, motor oil, and other pollutants that are prevalent in an urban environment. And the pollutants that I chose here, I mean, at least the modes of pollution that I chose here, they are laden with polycyclic aromatic hydrocarbons that contribute, of course, to urban sediment recontamination. And for all intents and purposes for this presentation, I'm only going to be talking about organics and specifically, PAHs. Now, the scope of the project was to assess the effects that runoff has on recontaminating the receiving sediment. Okay. Anybody has any questions so far? Okay. At any point, if anybody has questions, I don't really like monologues in general, unless they are from Morgan Freeman. But if anybody has questions during the talk that I give, feel free to interrupt me, and I'm always happier to have a discussion about something. Okay. Now, the sampling site where this project took place was Paleta Creek, at the last part of Paleta Creek, at the Naval Base San Diego in California. And this location down here, and actually many parts of the San Diego Bay, they are designated as toxic hotspots by the California State Water Board due to the contamination of sediments and benthic community impacts. Many of these impacts are originated from PCBs, and but PAHs is, as long as there is a gasoline-driven petroleum hydrocarbon economy present, they're always going to be PAHs. Okay, it's unavoidable. So the drainage basin that you can see on the right screen, on the right image of the Paleta Creek, is a typical residential area, but you can see two major highways traversing it. The one on the left is the I-5, and the one on the right is, if I'm not mistaken, it's 805, 405 or 805. So they are kind of atypical to have watershed with such big conveyance belts of automobiles traversing it vertically. And this was definitely taken into consideration later when we were trying to figure out what the sources of the pH are. Okay. The naval base is at the red square that I have on the right image, and it's just the last portion, the last part of the paleta of the creek itself. Now, to see a bit more in detail, in blue here you can see the creek itself, which is completely present within the naval base itself. Okay, and I have separated the sampling locations in yellow and red. So in yellow, here are the locations where we sampled the water, stormwater. And in red are where we sampled the sediment, the receiving sediment, within the San Diego Bay. So the locations 01, 02, 03, and 04, they are outfalls that were contributing runoff from specific segments of the base into the creek and the bay. The location C2 that you can see at the top is a sampling location that was upstream of the base, location C, and it's of the creek itself. C1 is the discharge point into the bay of the creek itself. And then the locations P17, P11, P8, and P1 are sampling locations within the bay, with increasing distance from the discharge point. Now, for the sampling methods, again, the stormwater part was sampled using 10-liter ISCO auto samplers. And those samplers were triggered automatically by sensors measuring flow velocity and salinity in order to ensure the collection of fresh water and minimize tidal effects. So it was automatically on and off when it was, based on the data that it was receiving from the sensors, to collect only water that was coming through the conveyance system, so fresh water. And the bioaccumulation studies that we conducted were performed with bent-nose clams of the Macomanasuta family, and they were both in situ, conducted by this device that you see here, which are the C rings. It's the sediment ecosystem assessment rings. But there were also ex situ studies happened where we collected sediment from the location, and we placed the organisms on top of the sediment in the lab, effectively. And next one was the pore water at those sampling locations was measured using SPME fibers, and which are passive samplers, effectively. And in the lower picture, the green one, you can see where the sampling rods were deployed besides the C rings themselves at the sampling locations. Now, of course, for the sediment itself, obviously we collected the sediment cores, but it was actually the sediment traps that we deployed that were the most useful, the data collected from the material that was collected in them, because they represent what is depositing from the water column, and they aren't mixed with last year's deposition, and they aren't affected by redistribution and bioturbation, all of these things. It's always fresh material that is depositing within the bay. And they show effectively what happened during the rain season itself. And here we have a layout of all the sampling periods overlaid on the storm events that happened in San Diego during the period of 2015 to 2017 when we collected the data. And as you can see here, there were multiple storms over this 2-year period, and 70% of them fall into 2 basic categories. Either about 1 to 1.5 inches of rain, or 0.1 to 0.2 inches of rain. So 70% of all rain events are in one of those 2 categories. So of the 2 storms that we sampled, Storm 1 was representative, was actually the biggest storm of 2015 to 2017, at least in total rainfall, with 2 inches of total rain precipitated, while Storm 2 was more representative of a small rain event with 0.16 inches of rain. Now, the sediment traps that I talked about were deployed into 2 periods. Were deployed for about a month in July 2015, and also for 4 months between October and February 2016. So, and effectively they collected material from 7 storms back then. The in-situ deployment of the SPMEs and the C rings, so for the passive samplers and the bioaccumulation studies, took place for about a month between January and February in 2016. The sediment cores were collected in 5 distinct periods, 5 distinct points in time, actually. Once in July 2015, then before and after the storm season, the 2015-2016 storm season, and then before and after the 2016-2017 storm season. And it's relevant to mention that the 3 years preceding that 2015 sampling were relatively dry up to that point, and this was of course taken into account during our analysis as well. Does anybody have any questions so far about our methods or the sampling periods? Okay.
Question in the chat. Can you see the question in the chat?
No, I cannot.
Yeah, so there's a question from Tom. Feel free to unmute yourself as well. Who's asking, he was curious about the Defense Department interest. Is it because the DoD properties are source of pollution, or because DoD or Army Corps of Engineers tends to dredge areas downstream of urban sources, or both?
Do you mind repeating the question? Actually, sorry, I think I'll be able to see it. Sorry. The department. So, very, very good question. Those $2 billion of liabilities that I mentioned before, they are of course on land of the DoD, and they are, most of them, they are legacy contamination that was generated, let's say, from the 20s, 30s, all the way to the 60s and 70s, before the EPA was formed, and before there was more environmental awareness, let's say. So the DoD has contributed to a lot of legacy contamination in many sites throughout the United States, and they are liable for that, and they are interested in remediating it. And the point of this project was to assess, if they clean it up, is it going to become dirty again? How quickly is it going to become dirty again? At least that's one of the aspects here. Did it answer the question? I'm not sure from Tom.
Yes, thank you. You did answer the question, and I have to say I posed it before you started in with your slides of San Diego, where I think you answered my question pretty clearly there too. Thank you.
Excellent. Thank you. Thank you very much for the question, Tom. Anybody has any other questions so far? I think we're doing very well on time. Okay, I'll move on a bit more, and I'll ask again later. So an important novelty of this project was the fractionation of the stormwater solids. So effectively, composited water, stormwater that was collected with the autosampler that I showed before, was split in 10 bottles using a Teflon decaport splitter. And in this graph that you see here, the splitter is that cylindrical device that I show kind of at the top here. Can you see my mouse cursor?
Yes, we can.
Okay. So it was split into 10 bottles, and you can see on the right they are plastic bottles that went into metals analysis. But for the sake of sanity and the reason and the time, I'm just going to focus on the left side, which are amber bottles, which is where the organics analysis happened, and the pHs that I'm going to be talking about. So this is what the decaport splitter looks like, and effectively mechanically just separates the 10 liters of sample that you drop into it into 10 equal as they can be sub bottles. And on the graph here, effectively you see that of the amber bottles that you generated here, each one of them was subjected to different filtration sizes. So let's say that the bottle on the left had the stormwater. We passed it through a 63 micron sieve, and we collected, of course, the water in another bottle with all the solids that were less than 63 microns. And then on the second bottle, it was less than 20 microns, less than 2.7 with filters, actually glass fiber filters, and 0.7. And this was a novelty of the project, and this allowed us to create these fractions. So dissolved clay, fine and medium silt, coarse silt, and sand silt, by actually figuring out the differential between the two particle sizes. We were able to determine how much of pH loading was in each specific fraction. And I will show, I think, on the next slide why this was important. And does anybody have any questions at this part? Okay, so I'm going to move to the results, and I will first talk about the stormwater sampling, about the stormwater itself. Okay, so the graphs here, they show the first storm on the left and the second storm on the right. The x-axis represent the solids fractions that I just talked about before, and the red bars indicate the concentration of solids in each of these fractions, and the blue bars represent the total pH concentration in each of those fractions. Okay. The first thing that stands out here is that the pH distribution from the blue bars, it does not follow the solids distribution, which there is no particular reason why it should follow it, but it's still a valid observation. And what we see is that the red bars here, which represent the solids, show us that most of the solids inside the stormwater that we collected was in the 2.7 to 20 microns. So it was in the fine silt range. But actually more than 50% of the total solids were into this fraction in both storms. But the highest load of PAHs was carried by larger particles and not those. And you know, this was interesting when we first looked at the data of this, because we tend to think of hydrophobic organics as being associated with the organic fraction, which typically is clay and fine silt. So organic contaminants, they like to attach, of course, on carbon particles. And since it's a surface sorption process, it will always disproportionately have a positive correlation with smaller particles, because you have a much larger surface area with larger particles. And I hope that is clear. So if you have 1 pound of clay, 1 pound of silt, and 1 pound of sand, because the particles are smaller in the clay, within that 1 pound, you're going to have many more particles, of course, and you're going to have much more surface area, so many more sites for the organics to sorb onto. But what we saw here on our results was, despite having smaller particles, you know, in the 2.7 to 20 micron range, most of the PAHs, about 70% of the PAHs, were actually in bigger particles, which is counterintuitive, and it was unexpected. And I've worked on projects since I joined Exponent, where I've seen, you know, the more logical thing. I observed the more logical thing of seeing that most of the pHs being associated with clay or fine silts, not with the bigger particles here. So this was very interesting, and of course, you know, we asked why did this happen? So we further investigated this strong association of PAHs with those large particles using scanning electron microscopy, imaging, and energy dispersive X-ray spectroscopy. And the images that I show here and the elemental analysis, they show that within the collected sediment, there were large carbon-rich particles that could be associated possibly with like chips of asphalt, of tire rubber, of pavement debris, and potentially coated also with motor oils and fuels, like I mentioned in the beginning. So you can see there is a large portion of carbon on those particles, and they are in the range that we're looking at, like over 20 microns. Some of them much longer, much bigger than that. Now, the images that I have here are actually from the filters that I talked earlier. So these are particles that were collected from the filters from the stormwater. These are not from the sediment that we collected in the traps or in the sediment cores. So this is effectively the material that you see here is the material that is transported with the stormwater. Okay, and specifically the stormwater that was exiting the creek, and these are the particles that are depositing in the San Diego Bay. Okay. Now, as the stormwater is discharged from the mouth of the creek up at the top here, you should show the solids that are coming with it begin to settle into the bay, and they are collected in the sediment traps that we deployed in several locations, you know, with increasing distance from the mouth of the creek. So the first graph that I'm going to show here, let's see here, is this graph shows the size distribution of the solids that were collected by the traps that we deployed during the wet season of 2015-2016. And the large particles of the stormwater are shown with the red and orange bars that you see in the graph. And you can see that those big particles of coarse silt and sand, which we saw earlier, are carrying most of the PAHs. They mainly deposited in the location P17, which is at the mouth of the creek. So I will it's a bit of a spoiler, but this is the first indication that we had that the effects of the stormwater or of the solids that are transported with stormwater are highly localized close to the discharge point. And they are collected by these traps, but mainly they deposit close to the mouth of the creek. Okay. The second graph I'm going to show is for the PAH mass that was collected within those sediment traps, and we kind of see the same, the same trend. Most of the PAHs that were transported with the PAHs were collected by the trap that was nearest to the discharge point. Let's see. So if we think of the particles that are coming with the runoff, okay, there's the runoff entering the bay. Due to the widening geometry that you see on the channel here, we would expect to see a decreasing trend in the collected mass as we get farther away from the mouth. So we would expect to see something like this, because the surface area on which the particles are depositing keeps increasing as the stormwater comes into the bay. So there is a less probability of collecting actually those particles in the traps that you have further away. So we would expect to see a trend like the one that I have here. But if we kind of synthesize as if there were two sources, it seems like the distribution that we see is the result of two imaginary sources, let's say. And so it appears as if there is a second source of particles that also leads to an increase of PAHs in location P1. Okay, and what could that source be? That could be resuspension from underwater currents that are acting within the San Diego Bay. They could be propeller wash from the ships that are operating in the bay. And of course, we had no control over shutting them down or restricting their movement. And you can see in the picture as well, like a simple barge, how much of a propeller wash it can generate. And also it could be bioturbation by organisms, benthic organisms living on the top 2 inches of the sediment. And the activities, the biological activities that they have, they always resuspend solids that they could also end up inside the sediment traps. But what we are noticing especially from the first graph, is that the big particles that we saw earlier that have a lot of PAHs with the stormwater, again, we see them localized close to the mouth of the creek. because they settle mainly in the near field. Does anybody have a question until this part? Okay, then I'm gonna move. Actually, yes, I'm gonna share this this graph as well here. So this observation that we did about the association of PAH with the near field was reaffirmed by the diagnostic ratio that I have here of anthracene to anthracene plus phenanthrene, and these are of the collected particles. So the runoff is indicated by the C1W here, has a weak pyrolytic signature that you see, and this material that is coming from with the stormwater is depositing into location P17 based on the things that I've shown you so far. And we see that there is, they're not exactly the same, of course, but there is similarity between the two. Keep in mind that always you're never, well, there are situations where you can have, but mainly in a complicated environment, such as an urban environment, you're never going to have only one signature, like you're going to be only pyrolytic or only petrogenic signature. It's always a mix of particles that are carrying either one, the other, or both signatures at the same time. So what we see is kind of an averaged out view here. So on the other hand, we see that the particles in the outer traps in P11, P8, and P1, they have a similar signature between them, which is much more pyrolytic in nature. And to summarize here, which is, we only talked about the stormwater so far, which is has been our focus. The large particles that are carried by the stormwater, they have the most PAHs and they settle in the near field. This is what I want you to take from everything that I've said so far. Okay. Now, to expand a bit more on the forensics, what time is it? It's 12:35, so we still have some time. And so this is the graph that I brought from the previous slide. And to give a 1 minute overview a bit of PAHs, because I'm not sure how many of you have heard of it. PAHs are polycyclic, aromatic, always talking about rings, hydrocarbons. So when you go at the pump to put gas in your car, the smell that you get there is actually benzene, which is only one ring. So it's 6 carbons, and it's in a ring formation, and of course the assorted, the hydrogens that are associated with it. The PAHs are polycyclic, so instead of having only one benzene ring, you can see in the right picture you have many of them, and it's a whole family. It's not only the 16 that I'm showing here that are the priority pollutants from the EPA. They actually can become even more complicated than that. The ones that I have here, they have between 2 and 6 rings of carbons. Okay, so in an urban environment now, okay, petrogenic sources are, among others, spilled fuels, motor oil, and asphalt. They're more, they are derived mainly from petroleum hydrocarbons, processed but not combusted. Okay, and their characteristics that I have here, a few of them, they include abundance of low molecular weight, between 2 and 4 ring of PAHs, and low anthracene, which anthracene has 3, but due to the stability of that molecule, it requires more energy to be created, and you don't see a lot of it. So the process, the diagenic processes that generate petrogenic hydrocarbons are mainly geologic. So they take a very long time in great depths where, past material under high pressure is transformed into the pH that we see here, into the petroleum that we use throughout our civilization. And as for the pyrolytic sources, in cities, they usually are exhaust particles such as engine combustion byproducts, as well as wood burning, ash. And due to the high temperature of the genesis conditions, they exhibit an abundance of high molecular PAHs of 5 and 6 rings, more complex PAHs, and also they have a lot of anthracene. And looking again at the previous graph that I showed on the previous slide, the location P17 receives larger particles, like I've already shown, which also seem to be associated more with petrogenic sources. Now, another pH ratio that can give a bit more insight into the nature of pH sources is the benzoapyrene to benzoapyrene plus benzoepyrene. So these are two isomers of which the benzoapyrene is photolyzed in the atmosphere much faster than benzoepyrene. So it gives a sense of how weathered a particle is, how long a particle has stayed, under the sun, effectively, to the bare bones of it. And a ratio of less than 0.5 indicates, and the lower the more pronounced. This shows that the source has been photodegraded for prolonged periods of time. So from the graph here, the solids on the location P17, they appear to be more weathered. And I will get back to that in a second. The third graph that I have here is not a ratio that is reported in the literature, but it mainly comes from the idea of a paper that I read from McVitie. I think it's a 1988 or 89 paper. And effectively what he did is he went into very remote lakes away from civilization, and he collected sediment from the lakes. And what he found was that he found PAHs even there. And one of the conclusions that he made was that high molecular PAHs are encountered in large proportions in atmospheric particles. And so what I did here is I calculated the ratio of 2 PAHs with 3 rings, anthracene and phenanthrene, to 2 PAHs that had 6 rings, which is indenopyrene and benzo-GHI-perylene. And and what we see here effectively in all of these graphs, the main point that I want to make is that there is a similarity between the stormwater solids, that solids are transported by stormwater, and the solids that are collected, especially in trap P17. And they are distinctly different, from the signatures of the solids that are collected in the other traps. And we can have a very long discussion at this point why this is happening, okay? Because we see that there are large particles with a lot of PAHs that have more petrogenic signature in P17. They appear to be more weathered, and they appear to be less affected by atmospheric deposition. So one theory, at least that I have, is that the stormwater itself, the effect that it has on this system that we're examining here, is heavily localized at the mouth of the creek. And then, due to the highways being so close, and of course being an urban environment, you have atmospheric particles from exhaust, from automobiles, of course, operating throughout the area. And those, of course, they settle in a much wider area, including directly, of course, into the San Diego Bay. But also those are smaller particles, and they are more prevalent throughout. They blanket the whole area. So you can find them, they are more pronounced in the in the areas that are not affected by stormwater. Okay, that's what I want to say about this. Does anybody have any questions until this point? Okay. So I talked about all the PAHs that are coming with the stormwater or with aerial deposition and everything. But now we will see if there was a corresponding effect on bioaccumulation. You know, how available are these PAHs actually to organisms that are exposed to them into the, into the receiving sediment, which that is the point of everything in the end, right? If there is contamination, the point, you only look at it from the risk perspective to the ecosystem and by proxy to the effect that it can have on human health in the end. So what we see here is the ex situ PAH bioaccumulation on the bent nose clams that we used on our bioaccumulation studies before and during both storm seasons, the 2015-16 and 2016-17 seasons. So the y-axis shows the lipid normalized tissue concentrations. So effectively it just shows concentration of PAHs on the lipid part of the organisms. And one more thing that I wanted to note here is that in October 2015, we have an extra, instead of having only before and after the storm, the sediment cores that were collected, we actually did one extra experiment with the 2015 cores, where I will take one step back and I will say how this experiment worked is that we took a sediment core and we placed organisms on top of it, and we left them for I think it was 2 weeks or 4 weeks, and let them interact with the sediment itself, live their life, and then we measured how much pH was in their lipids. So we had cores from before the storms, we had cores after the storms, and we wanted to see if there's going to be any difference, if the storm season increases the tissue concentrations. And what we did in that extra step in the 2015-16 season was we took the core of before the storm season and we placed manually material from the traps that we collected. So it was freshly deposited material in order to see if that material actually leads to higher concentrations in tissue. Okay. Now we can see in general a trend of increasing concentrations as we move from 2015 towards 2017. But can that increase be linked to the runoff itself? If we look at the black bars only that show location P17, there is not a significant increase in tissue concentration during neither of the storm seasons. So in the first season, you see that there is a bit of an increase. On the second season, there is a bit of a decrease in concentration. So it's not conclusive from this aspect. Second, the addition of the trap material that was freshly deposited, and if it was very contaminated stormwater, it should show an increase, especially in location P17, of the observed concentrations in the organisms. But again, here we see that they are effectively the same. So there doesn't seem to be a direct cause of the stormwater, of the solids that are transported with the stormwater into increased concentrations for the organisms. And I think lastly, the biggest seasonal increases that you're going to see were in location P08, which is the light gray, before and after, and also before and after here during both seasons. But based on everything that I've shown you so far, the P08 is further out in the bay, and it does not appear to be, based on the things that I've shown you, as much affected by the stormwater itself. So it must be driven, these increases that you see here in the tissue concentrations must be driven by another process, which we did not examine. And I think, so in general, I would say despite the increased concentration that we see of pHs coming with the stormwater, there was not really a big observable effect on the concentrations of PAHs inside the tissue of critters that are living in that benthic environment, and they are directly exposed to that material as it is being deposited on top of them, let's say, poetically. And so I will stop this here. There was one more slide that I have on some other very interesting observations that we made on the use of the passive samplers, which I did not touch at all until this point, but I don't think I have time to talk about that at this point. So in general, the conclusions, going through the things that I shared with you, we saw that despite the runoff carrying mainly, the red bar that we saw, carrying mainly fine silt, more than 50% of the solids are fine silt, more than 70% of the PAHs that are coming with the stormwater are associated with large particles of coarse silt or sand. The second thing that we saw was that the sediment pH recontamination, so in the sediment, was due to stormwater, and it appears to be maximized close to the discharge point, as we saw directly from the measurements of total pHs, also as that is the location where most of the solids settled. And another conclusion that we had here was that the traps is the best tool when they are combined with the stormwater analysis. They are the best tool to assess the recontamination potential of stormwater and also to assess sources. All the graphs that I had with the pH ratios, and you can get much deeper than what I had here. These were very basic ratios, let's say, but still they paint a picture that is as clear as you want it to be, I guess. And these were from the physical chemical point of view. From the biological point of view, we saw that despite all the recontamination and all of the pH that are coming with the stormwater and they are settling in P17, even despite all of that, these pHs are not bioaccessible, and they're not bioavailable to the critters living there. And that can go back to the SEM image that I had before. So we saw big particles that had a lot of carbon and a lot of pH on them. So I would theorize that those particles, they are very tightly binding the pHs, and because they are weathered as well, they are much more difficult for them to be extracted by the lipid tissue of an organism. So they don't pose risk effectively, or they don't pose a lot of risk. And this was the last thing that I did not talk about. Very briefly, if I will say something, was that measuring pore water had a much better correlation with the lipid concentrations that we measured than the sediment concentrations. And even to this point, from what I know, the EPA mainly, when you're doing an assessment of sediments, you are measuring, you're taking bulk sediment and you're doing a chemical analysis of it. And from that, based on bioaccumulation factors, we are deducting what the risk is going to be, and we are predicting what the concentration is going to be on living tissue. But many times this method is not accurate, especially when you have sediment that has a lot of carbon on it, or black carbon that also is coming out from soot in an urban environment, and it tightly binds pHs. And although when you use solvents, you can extract it from the black carbon, but the organisms cannot. So you have a bit of a disassociation between measured perceived risk and actual risk. But the graph that I had here, that was a correlation between the pore water measurements from passive samplers and the tissue concentration measured, they show a much tighter relation, which effectively that tells that the organisms, they don't necessarily see the high concentrations in the sediments that we might be measuring. They're actually seeing much lower concentrations that are existing in the pore water between the sediment particles. And that is, at least that's what our study showed, that it is a very good predictor. And so it can be a very good tool using passive sampling in order to predict, biota concentrations. So that was it. I would like to thank, of course, all the contributors that made this project work. For me, it was 4 years. It was most of my PhD was the work that I showed you into such few slides. And so there were people from Texas Tech that worked on this. There were people from SPAWAR Systems that actually did most of the sampling efforts on the San Diego Bay. And also there was Geosyntec was involved into this project, and also Dr. Robert Pitt and Dr. Alan Burton, which if any of you are dealing with sediments, you know, I'm sure many of these names are familiar to you. It's like a closed circle of people that you just come across frequently when you're dealing with sediments. And I will leave you with a couple of pictures from the Paletta Creek further upstream, and you know, some interesting characteristic that it has is the conveyor belts of stormwater. And thank you very much for your attention. And if you have any questions, I'll be happy to answer.
Thanks, Dimitri. I think there is a question in the chat. If you want to take that one, and then we'll see if other people have questions.
Do you know the DoD? Do you know how the DoD will use this data moving forward? Are they still considering putting treatments or some BMPs in place to lower the pH from the stormwater, despite the study found no significant correlation between the pH bioaccumulation in clams versus stormwater runoff concentration? Excellent question. So if you go to the CERDA PSTCP site, you'll actually see that there is a study, especially on BMP effectiveness. And I think that study started shortly before I left Texas Tech University. And it is continuing by Dr. Danny Ribel. And they are assessing BMP implementations that are in place in different bases, you know, Army bases throughout the United States. So they're measuring what is coming into the BMP, what is leaving the BMP, and trying to determine the effectiveness, you know, on different particle sizes as well as total PAH loads. And of course, they're looking at metals and PCBs and pesticides and other things as well. Anybody else? Well, thank you very much, Steve. One more thing, if I can say here, is that, you know, like I said in the beginning, sediments are a big liability for the Department of Defense, and they want to do something to remediate it. But before you remediate, it's wise to make a small investment into research that can give you some insight on what is the potential of the thing that you cleaned up being contaminated all over again, and you know, the time horizon and all of these things. But from me sharing the results that we had, you know, from this project, I was hoping that, you know, there's going to be a range of people that attended this presentation today. Some of you are going to be civil engineers. Some of them will have worked with or are working with stormwater. Some of you are working with sediments. So hopefully from different parts of the presentation, you can get, you know, maybe some insights that could give you some food for thought on maybe how to include some different things in your work that could make, you know, provide a more positive result, you know, to the local community where you apply your work, or of course to your clients.
Dimitri, I know you were recently in San Diego. Are you still involved in this project, or were you doing sampling for a different project?
No, I was in San Diego for a whole for different project in different part of the bay. This project, this specific project, the ER 2428 is over. And if you Google ER 2428, it's going to take you to the page where there is the final report, and you can take a look at all the results. There are metals as well if you're interested, PCBs. And yeah, Texas Tech still does research on the BMPs, like I said, but I'm not directly associated with them, even though I keep an eye on how this is going.
Any more questions or remarks to Dimitri? So if people want to get hold of you, Dimitri, can you put your email maybe in the chat for people to get in touch with you if they have questions or any follow-up remarks? Perfect. So if we don't have any more questions, I'd like to thank Dimitri one more time for an excellent presentation and really insightful talk. So with that, we will conclude our September meeting, and I would also like to invite you to our October meeting next month on the 13th. There'll be an invite for that meeting where we are planning on having a special meeting. It will be a joint meeting with the ASCE Seattle Section. It will also be a virtual meeting, but we will have Dr. Rebecca Newman from the University of Washington who will talk about her research in arsenic contamination of food, water, plants, and animals. So sounds like a very interesting topic. Be on the lookout for an email and an invite to that meeting. And with that, that's all I have. Again, thank you so much, Dimitri, for your talk, and we'll see you all next month.
Thank you very much, Simon, and thank you everybody for attending.